to our YouTube channel Naraj Academy. The main aim of this lecture is to discuss about the communication systems prelims questions of the IES or ESE exam in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button so whenever you upload new video, the direct notification comes to mobile. If any improvements needed in our lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. So why to waste more time? So let's get started. So now we are going to discuss the 161 question. See the question here. A source delivers symbols x1, x2, x3 and x4 with the probabilities 1 by 2, 1 by 4, 1 by 8 and 1 by 8 respectively. So the entropy of the system is. So here in this question they are going to give the 4 message signals, or we can say there are the 4 symbols. So therefore now for each and every symbol or the message signal, the probabilities are also they have given of 1 by 4, 1 by 8 and 1 by 8. So based on this we have to find what is the entropy of the system. The unit of the entropy of the system is, which is bits per messages or number of symbols. So therefore for each and every message or symbol, how many number of bits we are going to represent, that is called as the entropy. So we have to find what is the value of the entropy we need to figure out. So what are the 4 options? Option B is the correct solution of this question. So let's solve this numerical. So in this question they are given a 4 symbols, or we can even tell these are called as the messages. So for each and every symbol, how much is the amount of probability they have given, which is P1, P2, P3 and P4, which are going to associated with the symbols x1, x2, x3 and x4. These are the values. So now based on this we have to find what is the total entropy of the system we need to figure out. So basically the relation which is going to relate between the entropy and the probabilities of the symbols is, which is total entropy is equal to summation of I is equal to 1 to L, means the number of symbols. Let me assume there are L number of symbols, so therefore I is going to vary between the 1 to L, which is Pi log to 1 by Pa. This is a basic relation which is going to relate between the entropy and also the number of symbols with respect to the probabilities. So here the unit of the entropy, which is number of bits per messages or symbol, means for each and every symbol how many number of bits we are going to represent, that is the H is going to tell you the relation between the number of bits per the message or symbol. That is the unit of the entropy. So here if you see carefully, there are only 4 message signals, or we can say only there are 4 symbols. So now here L is going to become now 4 because there are only 4 symbols. So I is equal to 1 to 4, Pi log to 1 by Pi. So I am going to expand this formula. So therefore this is P1. So when I is equal to 1, we are going to get this expression. When I is equal to 2, this is the expression we are going to get. When I is equal to 3, we are going to get this expression, and when I is equal to 4, we are going to get this expression. So blindly substitute those values. So P1 is 1 by 2, so here also 1 by 2, and P2 is equal to 1 by 4, substitute here, and P3 is equal to 1 by 8, and P4 is equal to 1 by 8. So 1 by 1 by 2, so we are going to get log 2 base 2. So here 1 by 4, we are going to get log 4 base 2, and again log 1 by 8 with base 2, we are going to get log 8 base 2, and here also same thing, log of 1 by 8, we are going to get log 8 base 2. So here log 2 base 2 is going to value 1. See, log 4 with a base 2, so we can expand this 4 in terms of 2, which is 2 square. So this 2 is going to come here, so 2 by 4, again log 2 base 2 is 1. So similarly here also 8 we can represent by 2 to the power of 3. So 3 is going to come this side, which is 3 by 8, again log 2 base 2 is value is 1. And also here also I am going to replace 8 by 2 cube, so therefore this 3 is going to come here. So finally log 2 base 2 value is again 1. So if we do the summation of each and everything, finally we are going to get the value 1.75. so therefore 1.75 is the total entropy of the system, and also its unit is bits per symbol. So for each and every symbol this many number of bits are being utilized. So therefore this is the total entropy of the system when the number of symbols with their respect to probabilities which are given here. So now we are going to solve the 162 question. See the question here. To permit the selection of 1 out of 16 equiprobable events, the number of required is. So in this question they are given the total number of events or outcomes is 16. So based on this here now we have to find what is the number of bits we are going to take it here. So what are the 4 options? Option D, 4 is the correct solution of this question. So let's solve this numerical. So in this question basically they are given the total number of events is 16. So we can say the number of events means the number of outcomes also. So based on this we have to find what are the number of bits So how many number of bits? Because of these bits we are going to get the event of 16. So if you see carefully here, the relation between the number of outcomes or the number of combinations and the number of bits is, suppose that if there are n bits, so with respect to n bits we can figure out 2 to the power of n number of outcomes. So 2 to the power of n number of outcomes we can easily get here. Suppose let me assume if there are 4 number of bits, so therefore now we are going to get 2 to the power of 4, which is 16 outcomes. So we can say when the outcomes are 16 or the events are 16, the total number of bits required is 4. Suppose if the number of bits are 2, then we can get the number of outcomes is equal to 4. So you can write in another fashion also. Here the number of bits is equal to log events with respect to base 2. So even by this formula also we can figure out this value. So therefore log, which is the number of events, is 16, so therefore base 2. So 16 I can represent with respect to the 2 to the power of 4. So this 4 is going to come here, which is to this side. So 4 log 2 base 2. So log 2 base 2 is value is 1. So therefore 4 into 1 is equal to 4. So therefore the number of bits required is 4. So either you can go by this method or either you can go by this formula. So always you are going to get the same result. So therefore if the total number of outcomes or the events are 16, so in order to represent that, the number of bits which are required, which is 4 bits. So now we are going to solve the 163 question. So the question here, a communication channel has a bandwidth of 100 megahertz. The channel is extremely noisy such that the signal power is very much below the noise power. So what is the capacity of this channel? So in this question they are given that the channel, so whatever the communication channel which is going to have a certain bandwidth which is 100 megahertz, and also they are telling that in this channel the signal power is very much low when compared to the noise power. Means the this channel is going to have a lot of noise when compared to the signal power. So therefore now based on this data we have to find what is the capacity of this channel. We need to figure out, means how many number of bits per second are being transferred by this channel we need to figure out. So what are the 4 options? Option D, which is nearly 0 bits per second, is the correct solution of this question. So let's solve this numerical. So in this question basically they are given that the bandwidth of the communication channel is 100 megahertz, and also they told that the signal power is very much low when compared to the noisy power in this channel. Means S is called as the amount of power which is present in the message signal, and N is called as the power which is present in the noise. So in this question they are given that the N, the noisy power, is very much higher when compared to the signal power. So we can assume it is the ratio of S by N will be nearly equal to 0, because the denominator value is very high when compared to the numerator. So we can consider it is equal to nearly 0. So now we know the relation between the channel capacity. So channel capacity we need to figure out in this numerical. So we know the relation between the channel capacity, bandwidth, and the signal to noise ratio, which is channel capacity is equal to bandwidth log with base 2 with respect to 1 plus S by N. So suppose if you want to write this formula in terms of the log base 10, so this is the modification you need to do with respect to the previous formula. So you have to multiply with 3.32 bandwidth log 1 plus S by N with the base 10. So this formula is called as the Shannon-Hartley law. So the Shannon-Hartley law is going to give you a relation between the channel capacity, bandwidth, and also signal to noise ratio, means the amount of signal power with respect to the noise power. So here the unit of the C, the unit of the C is nothing but, here the dimension of the channel capacity is number of bits per second, means in 1 second how many bits are being transferred through this communication channel. That is what we need to figure out. So here I am going to use this first one. So therefore you can either use the second formula also, but I am going to use the first formula. So therefore C is equal to B into log 1 plus S by N with the base 2. So I am going to substitute the value of the bandwidth, which is 100 megahertz. So 100 into 10 to the power of 6 log base 2, as S by N value is 0, so therefore 1 plus 0. So 1 plus 0 is nothing but again 1. So log 1 with the base 2, its value will become 0. So any non-zero into 0 is going to lead to an answer which is 0. So therefore we can say the channel capacity is equal to 0 bits per second. So in this communication channel there is not even any information is transferred, because the noise power is very higher, means the receiver is not going to receive any message signal, it is only going to receive the noise signal. So we can say the channel capacity is 0 bits per second is the correct solution of this question. So now we are going to solve the 164 question. See the question here. A source produces 26 symbols with equal probability. So what is the average information produced by this source? So basically here they are given that a source or transmitter is going to produce a 26 symbols, so with equal probability, means for each and every symbol the probability is same. So therefore now with this data we have to find what is the average information. The average information is also called as the total entropy, means how many bits per symbol. So for each and every symbol how many bits we are going to represent. So that is what we need to figure out in this question. So what are the four options? Option D, between 4 and 6 bits per symbol is the correct solution of this question. So let's solve this numerical. In this question basically they have told that the source is going to generate a total 26 number of symbols. So total symbols which are generated by the source is 26, and also they have told that for each and every symbol the probability is very same. So we have already know which is summation of all the probabilities. So summation of all the probabilities has to be equal to 1. So which is P1, P2 up to 26 signals of P26 is equal to 1. So in this question they are given that each signal or each message or each symbol has a probability of same. So therefore I am going to assume all these values are equal to P. So P plus up to 26 times we have to do the addition, which is equal to 1. So we can write it is 26, P is equal to 1. So therefore P is equal to 1 by 26. So we can say each symbol has a probability of 1 by 26. So based on this data I have already told you the entropy formula, which is called as the total entropy. Average information means the number of bits for symbol, how many number of bits per symbol which are being utilized. It is called as the entropy, or we also call it as the average information. So therefore the relation between the average information and the probability for each and every symbol, which is H is equal to sigma I is equal to 1 to L Pi log 1 by Pi with respect to base 2. Here L represents the number of symbols. So we have to do the summation up to number of symbols. So I am going to assume here, see here in this question they are given that here each and every symbol has the same amount of probability. So therefore Pi is equal to, I am going to assume its value is P, because for each and every symbol its probability is P. So we have to do this addition up to 26 times. So therefore if you do the addition up to 26 times means L number of signals. If there are L number of signals means you have to do for the L times of addition. So therefore finally this formula is going to, we are going to get, which is L into Pi. So Pi into log 1 by Pi with respect to, but I have already told you Pi is nothing but P. I am going to assume each and every signal has the same amount of probability. So this formula is going to converge to this one. So therefore this formula is going to converge to this formula only when if all the signals have same symbols, or if all the symbols have same probability, and also here then this is going to come to in this fashion. So therefore L is called as the number of symbols, which is 26, and the probability of each and every symbol, which is 1 by 26. So here P is 1 by 26. So if you do this one, 26 get cancelled. So 1 by 26 means we are going to get here 26. So therefore log 26 with respect to base 2, which is 4.7. So therefore the total entropy, or we can say the average information, is 4.7 bits per symbol, means for each and every symbol we are going to use this many number of bits. So therefore here if you see the options, this 4.7 is going to lie between the 4 and 6. So 4.7 is going to lie between the 4 and 6. So this is in the option D. So therefore we can say option D is the correct solution of this question. So now we are going to solve the 165 question. See the question here. A source alphabet consists of n symbols with the probability of the first two symbols being the same. A source encoder increases the probability of the first symbol by a small amount E and decreases that of a second by E. So after encoding the entropy of the sources. So basically here there are n symbols, and also out of these n symbols they have told that the probability of the first two symbols is same for the first case. Then we are going to get some entropy. Then after, what they are going to do is they are going to increase the probability of the first symbol by small amount of quantity. Let me assume its value is E, and in the same manner by the same quantity we are going to decrease the probability of the second symbol. So based on this we are going to get the new entropy. See this new entropy, whether it is lesser than the previous one, or whether it is more than the previous one, or whether it is equal, we need to figure out. So out of the four options, option D, decreases, is the correct solution of this question. So let's solve this numerical. So in this question they are given that there are n number of symbols. So for simplicity I am going to assume the n is equal to 2, means only two symbols are present. So in the first case they are given that the probability of the first two symbols is same, so therefore there are only two symbols, so therefore the probability of each symbol should be half, which is 1 by 2 and 1 by 2. Then only we can get the total probability is equal to 1. So now based on this I want to find what is the entropy I want to figure out. So therefore here the relation between the entropy and the probabilities, which is H is equal to sigma I is equal to 1 to L Pi log 1 by Pi with respect to base 2. Here L means up to number of symbols. So there are only two symbols. So I am going to use L is equal to 2. So therefore we have to do only twice here. So which is P1. So we can write here which is C is equal to P1 log base 2 1 by P1 plus P2 log 2 1 by P2. So here we know the value of P1 and also we know the value of P2. So substitute them 1 by 2 log 2 1 by 1 by 2 plus 1 by 2 log 2 1 by 1 by 2. So 1 by 1 by 2 it is going to give you answer 2, and here also 1 by 1 by 2 we are going to get 2. So log 2 with respect to base 2 is 1. So 1 by 2 into 1 is 1 by 2, and here also log 2 with respect to base 2 is 1. So 1 by 2 into 1 will become 1. So half, so therefore half plus half is nothing but 1. So we are assumed that the number of symbols is 2 with equal probabilities. We are going to get the total entropy is equal to 1 for the first case. So now in the second case here they have told that the probability of the first symbol is increased by some factor and the probability of the second symbol is decreased by the same factor. So here initially in the previous case initially the probability of which is 1 by 2 means which is 0.5, and here probability of the second symbol is also 0.5. So I want to increase P1 by same quantity and decrease P2 by same quantity. So let me assume that same quantity is equal to 0.05. So I want to increase P1 by 0.05, which is 0.5 plus 0.05. We are going to get 0.55. So I want to decrease the second probability by same quantity as the previous one. So therefore 0.5 minus 0.05 we are going to get 0.45. So this is the quantity I am going to assume. They have so you can take any value. You can take either 0.03 or any value. So for simplicity I am going to take here 0.05. So these are the new probabilities we are going to get for the second case. So based on this I want to figure out what is the entropy of the source. So same formula, entropy is equal to sigma I is equal to 1 to L Pi log 2 with respect to 1 by P1. So here now there are only two symbols. So there are only two symbols. So we are going to get like this fashion. So we know the value of P1 and also we know the value of P2. So substitute them and finally we are going to get 0.98. So we can conclude that for the first case the entropy value is 1, and for the second case the entropy value is 0.98, which is lesser than the previous one. So we can say that so because of increasing probability of first by some factor and decreasing probability by by the same factor, we are going to get a entropy which is lesser than the previous one. So by increasing the probability of the first symbol by some factor and decreasing the probability of the second symbol by same factor for the n number of symbols, so the entropy is going to decrease when compared to the previous case. So we can conclude that the entropy is going to decrease. So now we are going to solve the 166 question. See the question here. If the probability of a message is 1 by 4, then the information in bits is. Suppose there is a message with a probability of 1 by 4. So here now we have to write what is the information, means in terms of bits we need to figure out. Means how many bits are going to represent here. So out of the four options, option B, which is a 2-bit, is a correct solution of this question. So let's solve this numerical. Basically in this question they are given that the probability of the message or the symbol is 1 by 4. So based on this we have to find what is the information in terms of the bits we need to figure out. Means we can represent this probability of this message signal in terms of how many bits we can represent this one. So it is called as the information we need to figure out. So the basic relation between the information and the probability, which is I is equal to log 1 by P with respect to base 2. It's a standard formula. So we know the value of P. The only thing is we have to know what is the value of the I. So the unit of the I is bits. So the unit of the I is bits. So we know the value of P and we have to know what. So we need to figure out what is the value of the information. So blindly substitute those values now here. So I is equal to log 1 by 4 with respect to base 2. So 1 by 4 is nothing but 4. So log 4 base 2. So 4 we can write. So 4 we can write, which is 2 square. So this 2 is going to come here. So 2 log 2 with respect to base 2. So log 2 with respect to base 2 value is 1. So 2 into 1 is equal to 2. So we can say the information is equal to 2 bits. So a message signal of probability 1 by 4 we can represent in terms of the number of bits is 2. So therefore this is the correct solution of this question. So now we are going to solve the 167 question. See the question here. A conventional telephone line with a 3 kHz bandwidth and having 30 decibels is signal to noise ratio. So can carry information at a rate. So basically there is a telephone line. So for this the bandwidth is 3 kHz. So and having 30 decibels. So dB, 30 dB signal to noise ratio. So signal to noise ratio is given in the terms of the dB. So here now based on these two things we have to find what is the information. So therefore this channel can carry an information at a rate means what is the channel capacity means how many number of bits per second are being transmitted through this telephone communication line we need to figure out. So what are the four options? Option A, which is 30 kilobits per second, is the correct solution of this question. So in this question they are given that the bandwidth of the telephone channel is 3 kilohertz and also they are given that signal reported noise power in terms of dB which is 30. So based on this we have to find what is the channel capacity means how many numbers of bits per second are being transferred through this channel we need to figure out. So I want to convert this dB in terms of the actual value. So therefore here 10 log base 10 S by N is equal to 30. So this is the conversion from dB to Sn. So here 30 by 10. So if this 10 goes this side, so we are going to get here 30 by 10 which is 3. So again this 10 is going to come here. So therefore we are going to get signal to noise ratio. The actual value is 10 to the power of 3. So now we have to find what is the channel capacity means the number of bits per second are being transferred through this telephone channel we need to figure out. So the basic relation between the channel capacity, bandwidth and the signal to noise ratio, which is C is equal to B into log 1 plus S by N with a base of 2. So therefore here we can convert this base 2 with respect to 10 by using small conversion. After doing that we are going to get here 3.22 bandwidth into log 1 plus S by N with a base 10. So now this is called as a Shannon-Hartley law. So therefore now I am going to use this relation to solve this numerical. So therefore here C is equal to 3.22 into bandwidth into log 1 plus S by N with a base 10. So if you see carefully here 3.22 bandwidth is 3 kilohertz. So therefore 3 into 10 to the power of 3 log 1 plus S by N value is 10 to the power of 3. See 1 plus 10 to the power of 3 is nearly equal to 10 to the power of 3 because 10 to the power of 3 is very huger than the 1. So therefore we can assume that 1 plus 10 to the power of 3 is nearly equal to 10 to the power of 3. So based on this here, see log 10 to the power of 3 with base 10. So this 3 is going to come here. So therefore we are going to get 3 into log 10 base 10. So log 10 base 10 value is 1. So therefore 3 into 1 is nothing but again 3. So if you do the multiplication we are going to get 28.98 into 10 to the power of 3. Now we can nearly equate it to. So nearly we can equate it to 30 into 10 to the power of 3 bits per second. So therefore here 30, this is 30. So 10 to the power of 3 we can add kilo. So kilobits per second. So we can say 30 kilobits are being transferred in 1 second through this communication channel, through this telephone channel when the bandwidth is 3 kilohertz and the signal to noise ratio is 10 to the power of 3. It means the signal power is very higher when compared to the noise power. Suppose if the signal power is very less when compared to noise power, then by default we can say the channel capacity is 0 because S by N value will become 0. So whenever the signal power is higher than the noise power, then only the signal is being transmitted through this channel. But if the signal power is very less when compared to noise power, then the signal is not going to transfer through this channel. So now we are going to solve the 168 question. See the question here. The ratio of signal to noise ratio of the wideband FM with respect to signal to noise ratio of AM for 100% modulation with identical total transmitted power, where MF is the modulation index of the FM. So basically in this question they are telling that the total power for this both the for the wideband FM and also AM is same. The total transmitted power by the signal which is same in the wideband FM and also in the AM. So based on this we have to find what is the signal to noise ratio of the wideband FM and signal to noise ratio of the AM when the AM signal has a 100% modulation, where MF is the modulation index of the wideband FM. So therefore based on this data we have to find what is the ratio of this one. So what are the four options? Option A 9 by 2 MF square is the correct solution of this question. So let's solve this numerical. So basically here signal to noise ratio of the wideband FM is equal to 3/2 beta square into signal to noise ratio of the input. Yes, this I have derived in my previous lectures. So therefore here also signal to noise ratio for the AM, which is m square by 2 plus m square into signal into signal to noise ratio of the input. Yes, these two relations I have already given in our notebook, or in the previous class also I have told regarding this two things. So basically here in this question they are given that the AM modulation is going to have a 100% modulation, means the modulation index is 100%, means the M value will become now. So beta is called as a modulation index for the wideband FM. So for the wideband FM always beta value will be very higher than 1. So here in this question they are assuming that beta is equal to MF. So they are going to assume beta is equal to MF, which is called as a modulation index. So but in our course we are going to use beta as a modulation index, but in this question they have used MF as a modulation index. So therefore beta is equal to MF here. So now I want to find what is the ratio of these two things. So if you do the ratio of this one, so they are given that the total power is same in both the cases. So we can say the signal to noise ratio is same for both the things. So this get cancels. So the remaining these two things are going to get divided. So substitute m is equal to 1 and beta is equal to mf. So finally we are going to get 9/2 mf square. So therefore for 100% modulation with the same signal to noise ratio of the input, then for the output of the signal to noise ratio, output of wideband FM and signal to noise ratio of the output of AM, we are going to get here 9/2 into mf square is the correct solution of this question. So now we are going to solve the 169 question. See the question here. SI and S0 denote the signal at the input and the output of a linear network, and NI and N0 are the corresponding noises. So which one of the following is the correct expression for the noise figure of the network? So basically in this question here there is a linear network and also input. So for the input of this network there is some amount of signal power and also noise power, and similarly the output of this network will have some amount of signal power and also the noise power. So therefore now based on this we have to find what is the correct expression for the noise figure we need to figure out. So what are the four options? Option C is the correct solution of this question. So let's solve this numerical. So basically this is a linear network. So therefore here whatever the signal, it is going to contain two powers, which are the signal power and also some amount of noise power, and similarly the output of this network will also have the same amount of power, means some amount of signal power and also noise power. So here the SI is called as the input signal power, means how much amount of power which is present in the actual signal, and NI is called as the input noise power, means so for the input of this network there will be some amount of noise. So what is the power which is present in that noise is nothing but NI, and similarly S0 is called as the output signal power. So at output the actual signal we are going to get, so how much is the power which is going to present in that signal, so which is S0, and N0 is called as the output in the noise signal. So at output there will be some amount of noise, so what is the power which is present in the output, that is called as the N0. So basically now with this data we have to find what is the noise figure. So noise figure basic formula is, which is signal to noise ratio of the input of this network by signal to noise ratio of the output of the network. So signal to noise ratio means signal power by noise power, means SI by NI for the input and S0 by N0 for the output. So if you solve this one we are going to get here SI N0 by NI into S0. So therefore this is the correct solution of this question. So therefore the noise figure of this linear network is SI into N0 by NI into S0. It is the correct solution of this question. So this is the last question of this lecture. See the question here. For a bit rate of 8 kbps, the best possible values of the transmitted frequencies in a coherent binary FSK system are. So basically here we are going to use the coherent binary FSK system, means coherent schemes means the frequencies in the carrier are of integer value, means they are going to have different frequencies, but here the cycles are fully integers, means integer number of signals are going to occur in the carriers. So therefore now based on this frequency shift keying and also the bit rate is 8 kbps, so based on this we have to find what is the best possible values of the transmitted frequencies we need to figure out. So what are the four options? Option D 32 kilohertz and the 40 kilohertz is the correct solution of this question. So let's solve this numerical. So in this question basically they are given that the bit rate is equal to 8 kilobit per second, means for 1 second how many number of bits are being transferred, means 8 kilobits are going to transfer in 1 second. And also they are given that here they are going to use the coherent FSK. FSK means frequency shift keying, and also they are going to use the coherent scheme. So therefore coherent means here they are going to have integer number of cycles. So purely integer number of cycles are going to used in the carrier. So therefore here if you see here, this is the bipolar binary data of value 1 and 0. So this is going to termed as value 1 and this is going to termed as a value 0. So therefore for the value 1 we are going to generate a carrier signal of frequency, suppose f1. So for bipolar data value 0 we are going to generate a carrier signal of different frequency fc2. But always here we are going to use the coherent scheme, means we are going to get the pure integer number of cycles. So we are going to generate pure integer number of cycles in the both one domain and also in the 0 domain, but also frequencies are also different. So the frequency of this S1 of t I am going to assume in this range, and S2 of t is a signal in this range. The frequencies are also different. So therefore now here, but the time period is same. So therefore this TB, the total time interval is same for each and everything, which is for 1, suppose this is the time interval TB, so for 0 the total time will be TB. So therefore this is a F1 for the first S1 of t, and F2 is the carrier signal of the signal S2 of t for this range. So here RB is called as the bit rate, which is bits per second. So basically the formula, the bit rate is equal to 1 by TB. So this is the S1 of t. I am going to assume S1 of t is equal to a cos 2 pi f1 t, because for this one data we are going to have frequency f1. So therefore here this total, suppose for one signal the time period is t1. So the time period is t1. As I already told you, there are pure integer number of cycles, means pure integer number of cycles are going to get. So the total time tb is equal to k1 into t1. So therefore tb is equal to k1 into t1. So where t1 is the time period of the one cycle, but we are going to assume there are k1 number of or integer number of cycles. So I am going to assume k1 as a purely integer, so k1 into t1. So t1 we can write in another fashion, which is k1 into 1 by f1, this t1 is equal to 1 by f1. So therefore I want to write f1, so f1 is equal to k1 by tb. So 1 by tb is nothing but bit rate, which is k1 into rb. So therefore f1 is equal to k1 into rb, where k1 is called as the integer value, whether it can take 1, 2 or 3 or 4, it goes on, but it is going to be only integer value, pure integer value. So same thing we are going to go for the another range of bipolar data of 0. So here I am going to assume a signal S2 of t. So S2 of t is called a cos 2 pi f2t, because frequency is not different. So the total this with time is equal to, suppose this has a time period of t2. So as I already told you, coherent means the total integer number of cycles are going to exist. So therefore total time tb is equal to some integer number of cycles into t2. So therefore tb is equal to k2 into t2. So therefore t2 is equal to 1 by f2. The time period is equal to inverse of the frequency. So therefore 1 by f2. So I want to know what is the f2. f2 is equal to k2 by tb. So 1 by tb is called as the bit rate. So therefore k2 into rb. So therefore f2 is equal to k2 into rb, where k2 is also an integer value, pure integer value, 1, 2 and goes on. So but k1 is not equal to k2, means the number of cycles which are produced in the first domain is not equal to the number of cycles produced in the second domain. So therefore we can tell that the number of cycles should always not be equal. So therefore k1 is not equal to k2. So based on this concept, now we are going to solve the numerical. See here, this is the conclusion. F1 is equal to k1 into rb and f2 is equal to k2 into rb. So where k1 is not equal to k2, and these both are purely integers. So here, so I am going to write here k1 is equal to f1 by rb and k2 is equal to f2 by rb. So now let us see, there are 4 options, a, b, c, d. So from these options we are going to see the solution. So here option A, 16 kilohertz and 20 kilohertz. So in place of f1 take 16 and f2 20. So k1 is nothing but f1 by rb. rb value we know, which is 8 kilobits per second, means 8. So if you do the division, 16 by 8 we are going to get answer 2, pure integer, but 20 by 8 we are not going to get pure integer. So therefore this is a wrong option, because k1 and k2 are pure integer value. And similarly option B, which is f1 and f2 are 20 kilohertz and 32 kilohertz. So substitute here, in place of f1 20 kilohertz and f2 32, but rb is 8. So 20 by 8 it is not an integer, but 32 by 8 yes it is an integer, 4. So k1 is not an integer and k2 is an integer, but both have to be integer. So therefore this is also wrong option. So option C, 20 kilohertz and 40 kilohertz. So in place of F1, keep 20 and F2, 40. So bit rate is 8. So 20 by 8, it is again not an integer, but 40 by 8, yes, it is an integer of value 5. So therefore both has to be integer. So therefore this is also wrong option because K1 is not an integer value. And now take the last option D, which is 32 kilohertz and 40 kilohertz. So K1 is, so in place of F1 take 32, in place of F2 take 40. So 32 by 8 we are going to get 4 and 40 by 8 we are going to get 5. Yes. Now we got both as integers. K1 is equal to 4 and K2 is equal to 5. So therefore we got integer number of cycles for both the domains. For one domain we got integer number of cycles, and for the domain 0 also we have got the same different integer number of cycles. So but both are not equal. So therefore we can conclude that option D is the correct solution of this question, because here K1 is not equal to K2 and yet they both are integers, pure integers. Yes, these conditions are satisfied. These two conditions are satisfied by this frequencies domain. So therefore we can tell this is the correct solution of this question. Option D is the correct solution of this question. By this lecture we have successfully completed the 170 questions in a very detailed manner. And if you like the content of our channel, then please do like, share and subscribe our YouTube channel, and don't forget to press the bell icon button, so whenever we upload a new video the direct notifications comes to mobile. If any improvements needed in our video lectures, then please do comment in the comment section. We will definitely include all those improvements in the coming lectures. Thank you so much for watching this lecture. Keep smiling, take care and bye bye.